What specific problem does the FluxMusic method aim to solve in the context of text-to-music generation, and how does it fill the gap compared to previous approaches?
The FluxMusic method aims to address the inefficiencies and limitations of existing text-to-music generation approaches, particularly those relying on traditional U-Net architectures and language models. By introducing a transformer-based architecture that utilizes rectified flow training, FluxMusic enhances the generative performance and training efficiency compared to prior models like Music LM and Audio LDM2, which primarily use spectral latent spaces or discrete representations. The model integrates both textual and musical modalities through a double-stream attention mechanism, allowing for a more nuanced interaction between text and music, which previous methods often lacked. Additionally, FluxMusic operates within a latent VAE space of the MEL spectrogram, improving the representation of music and facilitating better noise addition during training. Overall, FluxMusic fills the gap by providing a scalable and effective framework that leverages advanced architectural designs and training strategies to achieve state-of-the-art performance in text-to-music generation.
Can you provide a detailed, step-by-step explanation of how the FluxMusic algorithm operates, including its unique components and any novel techniques introduced?
The FluxMusic algorithm operates through a structured process that integrates both textual and musical modalities for text-to-music generation. Initially, it constructs an input sequence by embedding text and noised music, where the noised latent music representation is flattened into patches. The model employs a double-stream block architecture, allowing independent processing of text and music through distinct sets of weights, which merge during the attention operation. Following this, a single stream block is utilized, focusing solely on music sequence modeling after dropping the text component, enhancing computational efficiency. A novel aspect of FluxMusic is its use of rectified flow training, which establishes a direct mapping between data and noise distributions, improving generative performance and training efficiency compared to traditional methods. Additionally, the model leverages multiple pre-trained text encoders to capture various levels of textual information, enhancing flexibility and performance during inference.
Could you illustrate the internal workings of the FluxMusic model using a simple example, such as how it processes a specific text input to generate a corresponding music piece?
The FluxMusic model processes a specific text input by first converting the text into embeddings using multiple pre-trained text encoders, such as CLAP-L for coarse features and T5XXL for fine-grained details. For instance, if the input text describes a calm piano melody, the model would extract relevant features from this description and concatenate them with a noised latent music representation, which is derived from a MEL spectrogram. The architecture employs a double stream block to maintain independent processing of the text and music modalities, allowing for a bidirectional flow of information. After this, the model transitions to a single stream block, where the text component is dropped, focusing solely on predicting the noised music patches. Finally, the generated music is reconstructed from the MEL spectrogram using a pre-trained vocoder, resulting in an audio piece that aligns with the original text input.
What are the theoretical or practical advantages of using FluxMusic over traditional diffusion models or other text-to-music generation methods?
FluxMusic offers several theoretical and practical advantages over traditional diffusion models and other text-to-music generation methods. Firstly, it employs a rectified flow training strategy, which enhances generative performance and training efficiency compared to conventional methods like DDIM, as demonstrated in the comparative analysis. Secondly, the architecture integrates a double stream block for independent processing of text and music modalities, allowing for a more nuanced interaction between the two, which is not typically achieved in U-Net-based models. Additionally, FluxMusic's scalability is evident, as it accommodates a wide range of model sizes and configurations, leading to improved performance with increased depth and width of the architecture. Finally, extensive experimental results indicate that FluxMusic achieves state-of-the-art performance across multiple objective metrics, as well as superior subjective evaluations in terms of overall quality and relevance to textual input, highlighting its practical utility in the audio industry.
How was the FluxMusic method validated, and what datasets and metrics were employed in the performance testing?
The FluxMusic method was validated through a comprehensive evaluation process that included both objective metrics and human assessments. For objective evaluation, several metrics were employed, including the Frechet audio distance, FAD, Kullback-Leibler divergence, KL, and inception score, IS, calculated using the audio LDM_eval library. The performance testing utilized multiple datasets, including the AudioSet Music Subset, ASM, Magnetagtune Million Song Dataset, MSD, and the Song Describer dataset, with a total training dataset encompassing approximately 22K hours of diverse music content. Additionally, human evaluation involved assessing the overall quality and relevance of the generated audio samples, with raters from both expert and novice backgrounds providing scores on a scale from 1 to 5. The results indicated that FluxMusic significantly enhanced both the quality of the music and its alignment with the textual input, demonstrating its effectiveness in text-to-music generation.
What specific results did FluxMusic achieve in comparison to existing models, and how do these results support its efficacy in text-to-music generation?
FluxMusic demonstrated significant advantages over existing text-to-music models, achieving state-of-the-art performance across multiple objective metrics, including Frechet audio distance, FAD, and Kullback-Leibler divergence, KL. In comparative analyses against models like Audio LDM2, Musai, and Music LM, FluxMusic not only outperformed these models in objective evaluations, but also received favorable subjective ratings in human evaluations, particularly in overall quality and relevance to textual input. The improvements in performance can be attributed to the rectified flow training strategy and the advanced architecture of FluxMusic, which effectively integrates both textual and musical modalities. Additionally, expert feedback highlighted substantial gains in quality, indicating the model's potential utility for professionals in the audio industry. Overall, these results underscore FluxMusic's efficacy in generating high-quality music that aligns well with textual descriptions.